This presentation is about our work on a fast configuration space algorithm for variable topology truss, modular robots. A large number of modular robots have been developed, and each module is usually in a regular shape, such as a cube or a sphere. While variable topology truss, or VTT, looks very different. It is in truss structure. Similar to variable geometry truss, or VGT, it is composed of multiple members and the intersections among members are nodes. A VTT can change its shape by changing the length of members, like a VGT, and this process is called geometry reconfiguration. Also, it can change how members are connected. This process is called topology reconfiguration. This is our hardware prototype doing a simple experiment that is to move a single node around. The node is controlled by 3 members fixed to the ground. Each member is a linear actuator using spiral zipper mechanism, with ends being reconfigurable nodes. An individual node can be split into 2 separate nodes, and reversely, 2 nodes can be merged into one. This process is the topology reconfiguration. The position of a node can be changed by changing the length of connected members. That is similar to controlling a parallel robot, and this is the geometry reconfiguration. In this work, we focus on geometry reconfiguration. We use an undirected graph to model a VTT. For any node, its configuration space is clearly R3, and the state of each member is determined by the locations of its 2 nodes. In order to do path planning for a node, we present a fast algorithm to compute its obstacle region and free space. In this work, we show that the obstacle region of a node can be fully determined by the states of all not connected members. There are 3 cases in total. In the first case, when Vi is inside the blue polygon, these 2 members will collide. Similarly, for the other 2 cases, when Vi is on any blue rays, collision will happen. In all of these cases, the obstacle region is determined by members which are not connected with node Vi, and this tells us how to find the whole obstacle region. To find all the obstacle regions, we just need to find all polygons generated by any neighbor of the node and any member that is not connected with the node, such as the purple polygon on the left. With this conclusion, we can find the obstacle region for a node which is composed of many polygons shown in this video. Even for this simple truss, the obstacle region for node V0 is super complicated. The number of polygons is of the square of the number of members in the worst case. Then the challenge is to find the free space that the node can reach without collision. The free space of a node may not be fully connected, and not all obstacle regions can affect the geometry reconfiguration motion of the node. For example, for this node V, these polygons are the whole obstacle regions, and the node is currently enclosed by polygon P1, P2, P3, P4, and P5. And the free space outside this region is separated by these polygons. Polygon P6 has nothing to do with the enclosed free space containing node V, where node V can move freely as long as its path is inside this space. Our goal is to find this enclosed subspace containing the current location of the node. There are 2 steps in order to find this space: polygon intersection and boundary search. Given all obstacle polygons, we first compute the intersections of these polygons to generate a new set of polygons and find the connections among them. If there are no intersections between 2 polygons, or they only intersect at a point, we can skip this pair. Other than these 2 situations, there are 4 cases we need to consider. The intersection can be a line segment, and this line segment may separate 0, 1, or both polygons into 2 pieces. Or 2 polygons are on the same plane and their intersection is also a polygon. We have to check every pair of polygons, so this process costs quadratic time complexity in terms of the number of polygons, namely the 4th order of the number of members. Then, we can run a boundary search algorithm to find the boundary of the free space containing the node. This algorithm starts from the polygon that is closest to the node, which is the red one PS here. The normal vector of the red polygon NS is pointing inside the free space. We first check one set of its neighbor polygons, which intersect with the red one on one of its edges. There are 2 polygons in this set in total, and the green one is the innermost polygon along vector ns. So the green one is added to the boundary. We will repeat this process for every edge of every polygon and stop until all polygons are checked to generate the boundary. Every polygon is checked at most once, so it takes the linear time complexity in terms of the number of polygons or the quadratic complexity in terms of the number of members to do this search. Then, with all the obstacle polygons, we can finally find the free space on the right. The node V0 can move freely to any location inside this free space without collision, as long as its path is inside the space. Once we have this free space, which is usually not convex, it can be decomposed into multiple convex cells. Inside any convex cell, the node can move freely without considering collision. Then we can have a complete path planning solution for this node. Given the initial location and goal location, we can apply a graph search algorithm to compute the traversed cells to generate an optimal path. For example, we want to move the node from the current location to a location inside this purple cell. The path planning result is that the node just needs to traverse 2 cells for this task, and it can move in a straight line from its current location to its goal location. The solution is deterministic and complete, namely it's 100% guaranteed to answer the path planning problem. We did some comparison with retraction-based RT, which is designed for a variable topology truss planning problem. All our tests are running on a computer with the 8th generation of i7 processor. We randomly pick a goal location for every node and compare the performance. Our method can solve the problem faster and the performance is guaranteed because it's deterministic. Most of the time consumed in our approach is for cell decomposition. We use CGAL library to do this, and it is the NP-hard problem to decompose a non-convex polyhedron into a minimum number of convex pieces. This process can be improved by using a faster decomposition method, but may end up with more cells. Here we show that we can also solve some extreme tasks. For example, we want to move this node to the other side of the truss, and it has to go to a very high location first in order to avoid the collision among those blue members, and then move down to the goal. The total planning time is about 0.8 seconds, and still, most of the time is spent by cell decomposition. We can also solve narrow passing problems easily, which is a known issue for RT type of planners. Here we command a node to enter a narrow space, and the total planning time is around 1 second, and similarly, most of the time is spent by cell decomposition. Because we can do path planning for a single node efficiently, the overall shape of a truss can be changed by moving node one by one. Then the multi-node planning problem is simplified a lot. We just need to find an order to move every node. The way we look for the order is just to try them in sequence, and if failed for any node, try next candidate node. Here we show a task to alter a truss in cubic shape to a tower. 4 nodes need to move, and it takes 4 seconds to do the path planning for all of the nodes. Here is another example to change a truss with an arm into a tower. In this test, 6 nodes have to move, and the total planning time is around 8 seconds. The drawback of this approach is that it may not be able to find a solution even if there exists one feasible plan. But this is an effective way to solve this highly coupled multi-node planning problem. The motion of nodes are highly coupled because changing the location of one node can significantly affect the obstacle region and free space of other nodes. This is the end of the presentation. Thank you for watching.